Let's begin. So today's training is about ICS OT cybersecurity. It's a foundational masterclass giving you some inputs to increase your knowledge. So InfoSec train, thanks to them for organizing this session, and I'm able to share my knowledge through this platform. Thank you again, InfoSec train. So we'll just breeze through this. Okay, so we are going to talk about critical infrastructure related cybersecurity, and it's very important that you understand the seriousness behind it. So whatever you're learning is basically from knowledge. So how you apply and use it, you should ensure that you are responsible and take care that be sure to consult with professionals before you do anything at your facilities and so on. And copyrights, of course, just wanted to be sure whosever logos or information that has been used is purely for educational purposes. All right, so this is John here. I suppose many of you might have already seen me on LinkedIn being active. So I have around 16 years of experience as an instrumentation and telecom engineer, and I transitioned into OT cybersecurity a few years back, and really glad to share my knowledge and learnings. All right, so this is the agenda for day one. So we have divided into 2 sessions. So it will be 4 hours or less than that. And OT, this is something you keep hearing again and again, right? Operational technology. So this is a very loosely termed word, but has become very prevalent to kind of anything that is non-IT, right? And this is applicable to almost all industries that you can see here, right? Oil and gas, energy, manufacturing, airport transportation, power generation, and so on. So what exactly are these? So before we go into the OT cybersecurity aspects, it is important that we know what are the industry sectors where OT is applied, right? And industries such as oil and gas, petrochemical, transportation, pipelines, these are something that are lifeblood of a nation, and hence they are designated as a critical infrastructure. And without them, the economy of the countries can come to a grinding halt if there is some stoppage of the production and so on. And because of this, they need to be continuously operating. So hence the significance. So as I was telling, there are a few different industry sectors that you might need to know. So manufacturing industry. So when we talk about manufacturing industries, manufacturing presents a large and diverse industrial sector, right? With many different processes, which can be categorized into process-based and discrete-based manufacturing. The process-based manufacturing industries are typically utilize 2 main processes. One is continuous manufacturing process, and another is batch manufacturing process. So when we talk about continuous manufacturing process, these process they run continuously and with some transition from one form of good to other, and they make different types of products. There's a lot of value addition being done. So typically these kind of continuous manufacturing process includes some kind of process that is happening, right? For example, a power plant or a petroleum production in a refinery, we get the crude oil and it undergoes various chemical process and different equipments, and we get the end product, and from that the various byproducts are kind of done, right? So this is continuous manufacturing, also called as a process industry. Then we have batch manufacturing. When we talk about batch manufacturing, this is very distinct when we compared to the process industry. So here, the processing steps are kind of distinct. They're conducted on a quantity of material, and there is a distinct start and end step to a batch process, right? Like for example, pharmaceutical, paint, right? These are called batch process, and there's a possibility of some steady state operation during intermediate steps. So food manufacturing is again one type of batch manufacturing, and there is another type of manufacturing where there are series of steps. It's called discrete manufacturing. These are usually like uh, material goods and so on, especially where there are a lot of components and assembly parts. And for example, machining, this is one type of industry. So automotive comes under discrete manufacturing. Fast moving consumer goods, iPhones, phones, laptops, these all come under discrete manufacturing. So the both the process based and discrete based industries utilize similar control system sensor network. How they are applied differs. So some facilities are a hybrid of discrete and process based manufacturing. So this ICS or industrial control systems are used to control geographically dispersed assets and often scattered over thousands of square kilometers, depending upon, like, for example, if it's a water distribution or a wastewater collector system and so on. Okay, so moving on to the next slide. Uh, we hear about OT systems and OT industries. Of course, I discussed just now. But what are the building blocks of OT system? Probably most of you might heard about the Purdue model, right? And there's always this level zero where the process is happening and there are sensors. But what are they? So the level zero that no one talks about. So these are sensors, transducer, switches, transmitters, and different kind of measuring devices. So they sense and provide some output. So I was talking about these sensors. So these sensors generally have an output of an analog signal or digital signal, and we still use some kind of instruments where pneumatic output also is still necessary. But originally, when the industry started, uh, we had a lot of pneumatic instruments doing all the sensing. So I'll give you some simplified definitions what a sensor is. So sensor is a device which translates a physical property. It could be pressure or a temperature, and it converts into an electrical signal. So this is sensor. So transmitter. So transmitter is basically a combination of a sensor and an electronic module, which helps the sensed signal to be transmitted to a longer distance, and hence a transmitter. A switch is something that holds a threshold X or Y, and uh, its output is either true or false kind of thing. So for example, if the pressure measured is 10 millibar, and we have set 10 millibar in the switch, then the output will be true. Otherwise, the output will be false. So that is a switch. So these definitions can be applied to any type of sensor, uh, and like temperature and so on, temperature, flow, level, and so on. So uh, when we talk analog and digital, so analog is a signal that is continuously variable as opposed to a range, like for example, digital. So a good example would be the clock that we have in our house, right? Analog clock, and nowadays, of course, there are a lot of digital clocks. So that is a good example. So what are the trends over time? From a pneumatic sensing, we have moved to electrical, where the output is in milliamps or millivolts or resistance, and then a combination of electrical signal with digital, um, um, something called HART protocol, where the instruments have the capability to transmit both the analog signal and the digital information. And now, of course, we have various communication digital signals that have their own protocols and the wireless. So originally, we used to have electromechanical relays and switches, and later on they developed into programmable logic controls or PLCs and various control systems. Right? All this has something to do with the security that we'll be more interested in talking about later. Why, we'll come over that. So what are the trends? If you see, uh, once upon a time it was hardwired and proprietary, and now the protocols, communication protocols, have become open and so on. And the communication, 10-15 years, almost every vendor used to have proprietary uh, protocols for the communication. Now there are open protocols, like for example Modbus and so on, and OPC UA. We'll be taking a look in the upcoming slides. So these are the various things that has evolved a sea change in the last 50 years, and they are becoming digital, they are becoming more reliable, and so on. So overall, the industrial automation is undergoing moving from hard proprietary systems to open systems, and this is basically driven by lowest cost of ownership, right? And of course, the capital expenditure needs to be minimal so that they can make more profits, and all these aspects have an implications on the security, which we'll be discussing. So the communication between various systems within the same plant, right? So these are becoming basically an open object standards based kind of interface. So the general architecture of the automation system is moving from a monolithic solution to a more of a scalable and modular system, right? So, as I was saying, the instruments are becoming more smart, and earlier used to be dumb, right? And now there are diagnostic inbuilt features which can prognose uh, what are the issues and so on, and it helps the operations and the maintenance and so on. Instead of having them to be replaced during shutdown, we can proactively order the components or get a replacement and so on. So these are the some of the field instruments that you see on screen. The one here, this is a control valve where it is pneumatically operated. This is a controller here. Uh, you could give a digital input or an analog input. It depends upon how you want, and make the valve body is bottom here. This is a controller here, and this is the actuator. This controller operates this actuator, and that's how you open close the valve. So the valve something looks like this. Basically they are doing some kind of factory testing, functional testing, that's what it is called. And we have a pressure transmitter, radars, temperature transmitters. All these are field instruments that is used in different industries. So coming to the building blocks of OT system, at a very basic level, this is how a control system works. What you see on the screen is a basic closed loop system. This is the block diagram. You sense, and the information is given to the controller. The controller takes the action. The actuator operates, and the plant does its own thing, and the feedback is given to the sensor, and the sensor is adjusted or calibrated as needed. So what is a control loop? What are you seeing? So control loops are something that are used in a industrial or automation systems, where their primary function is to monitor and control the devices that are involved in this process. So the system runs the hardware parts and the software control functions that are needed to measure and adjust the variables that affect the process. So as a process management needs, right? The process variables need to be set in a specific set point. Otherwise, uh, whatever that is being sensed or produced may not meet our requirements. So that is the main purpose of the closed loop feedback system. So the process variables could be many aspects, and uh, these can be basically programmable based on our requirements, some predetermined range or something. And so this control loop basically helps in measurement, comparison, and adjustments. So what are the different types of loop? What you are seeing here is a closed loop system, and they're also called feedback control system. So as I was saying, feedback loop is an essential component for this to assure that the performing action uh, of keeping the process variable at the same value at this as a set point as we need. So this is open loop that you see here. Basically, there is no feedback and hence called an open loop. Uh, so this is the type of control where the action is taken by this is the final control element, where the action of this controller is not dependent upon the uh, whatever is that is sensed. This means that output is not monitored and it's not fed back into the input for comparison. So basically, when a command is given to the controller, it sends out a signal to take action, and this controlling signal is put into a process that needs to be controlled. So basically, open loop systems do not have any checks and balances because they don't have a feedback system. So this means that the system is expected to follow the input command no matter what the end result is. So so basically, what we saw, what are the OT industry sectors, and what are the instruments, and what are the basic controls that happen. So now we are going to take a look at the main control systems that we call OT. So OT is not technically defined yet. A lot of committees, standard groups, they are still debating and haven't come to a conclusion yet. But it's a combination of all these terminology like DCS, SCADA, PLC, RTU, IED that we call as OT, right? So earlier we saw a basic loop, and this is a little bit this block diagram that you see here, where you can see the sensors. This is a control process. It could be a pipeline, it could be a tank or a vessel where there could be liquid. Here, this is sensor, and this sensors gives input to the controller. Controller takes action, and whatever is happening in the controller, this can be viewed at the human machine interface, which we'll be seeing in the coming slide. And in case there are some issues in the controller with respect to maloperation or some functional issue or errors, the feedback is given to the diagnostic maintenance management systems and so on. And in case if the controller is not working properly, we need to give some variance to the sensor so that can take a separate action. So the feedback is again given to the sensors. So many of today's OT systems evolved from the insertion of IT capabilities into the existing physical systems. I told you, right? Originally, we had electromechanical relays, and they slowly transformed into PLC. So, for example, embedded digital controls were replaced with analog mechanical controls in rotating machines and engines. So, what happened was this improved in cost and performance. So, that was the reason for this evolution. And the result is what we see now. Uh, the various smart technologies that is being adopted, right? Smart electric grid, smart grid, smart transportation, smart building, and so on. It all evolved from here. While this increases the connectivity and the criticality of these systems, the another issue that which we didn't notice for the last decade or two was the adaptability, the resilience, and security. Of course, safety was always a part of this. We will discuss on that in the upcoming slides. So, engineering of these OT systems continues to evolve, and the various new capabilities and maintaining typical long life cycles, right, when compared to ITs. But again, there are certain issues because of the interdependencies of safety, security, and privacy, and of course the environmental impact that has become more critical, or that needs to be managed, right? So what does OT stand for? OT is operational technology. It refers to the hardware and software systems used to monitor and control physical devices or processes in various industries. So, as I said, OT encompasses a wide range of technologies and components, including ICS, SCADA, PLC, TCS, and so on. So, the primary goal of OT is to ensure efficient and safe operation of the processes. So, it involves real time control, monitoring, and automation of the physical systems that you see here. So, by nature, uh, there is specific requirements of reliability and availability and safety due to the critical nature of the processes they manage, right? So, hence, safety and security is paramount. All right. So, that was a general block diagram that you saw. Uh, the one you see now is a basic model for a PLC or programmable logic controller. So, if you see, there's a power supply here, 24 volts or 120 volt VAC, and there is an input module, there is an output module. So basically, inputs carry signals from process into controller. They can be input switches, sensors, transmitters, and so on. While the outputs are devices that the PLC will send changes out to the system. It could be digital input or a digital output, either a potential free contact or a 24 volt DC voltage, depending upon what we want to operate and so on. So, not going to too much detail because of lack of time. And we have the CPU, the memory unit. Then originally this was it, but later on, once the Ethernet technologies developed, earlier we used to have serial communication, then Modbus, serial Modbus. Then with the advent of Ethernet, Internet protocol, and so on, there's a separate module for Ethernet and so on. So the CPU kind of acts like a programming device where programming functions are available, where based on the memory you can do some logic, right? The ladder logic or functional block diagram. Of lately, it has become more easy, like drag and drop kind of thing. You don't have to write ladder logic, but ladder logic is very interesting and quite easy to learn. There are a lot of free and open source tools as well. So this programming system is what is the brain of this PLC, where it uses binary language. zeros and ones, right? And this programming is done through a laptop or an external device where you need to plug in, and you have a application specifically for that model where you do the ladder logic and you compile it and you upload it into the controller. So this is the PLC. So here you see a PLC in terms of how it actually operates. So you have these different sensors here going in as field inputs into the PLC IO modules. This is not IO modules. The IO modules are here. These are the terminal blocks where you do the wiring. This is a good practice. You give it to the IO modules, and sometimes we have surge arresters or IS barriers here located here. They are for safety features, right? And from here, the different these IO modules all may not be same. It can be 8-bit, 16-bit, 32-bit, and there might be analog IO, digital input, DO, analog input, analog output modules as well, and um, like resistance, sometimes resistance for a RTD or a thermocouple. You need a specific module for that, and these are final control elements. It is a control valve, it's a motor, start stop of a motor or on off of a valve, and the feedback is again given. Like for example, if it opens or closes, we know there are limit switches here, or sometimes it could be a smart transmitter as well for the position. So it could be analog, it could be digital. So this input is given back to know the status, like for example, this is on or off or closed or open. So PLC is a digitally operated device. So basically what happens is we can improve the accuracy and speed of operation by using a PLC. So PLC would take inputs from devices, various devices and so on. At the heart of a small system, this is what majority of the small to medium sized manufacturing facilities based on the number of IOs use. Nowadays, the PLCs are available at a so low cost that even homes and we can do our own programming and switch on, switch off. There's a lot possible. The home automation has advanced and the cost has reduced a lot. All right. So that was about PLCs. So here we are, DCS, distributed control system, the darling of everyone. So what is the DCS and how does it operate? So in a DCS system, the total process would be divided into a certain number of subsystems. So each subsystem would be controlled by its own controller. And we can describe DC as a large process that is controlled by a certain number of controllers, and each of these controllers would control its own subsystem. So this basically would be divided across a plant in different areas, and each areas will be assigned a controller, right? And the whole system would be connected to a single control system. So it comes here. Means there are different controllers here, and this is basically the field wiring. From this is the process. These are the sensors, junction boxes on the field. The smaller junction boxes, then the bigger junction box. Then we have something called a marshalling cabinet, and from the marshalling cabinet we bring it here. The reason why we have is purely again a best practice, because like if it's a small plant it's okay, but if it's a huge plant you'll have thousands and thousands of wires running, right, of different configurations coming in, and it'll be a mess to directly connect. So this is a good practice. So any troubleshooting or maintenance, it'll be much easier to do. So basically the DCs will collect all the data from field, and it will utilize this data to control the specific process. So and uh, DCS is basically for monitoring purposes. The same DCS, when it's used for a different purpose like fire and gas or emergency shutdown, system or ESD, right? Uh, there some control actions will also be done. Of course, here also there is control action. I don't say it is not, but we do have some critical shutdown system which are kept separate from DCS. So they are called ESD. And there are fire and gas or any safety critical instruments or sensors related outputs also is not given to DCS. So it is given to a FGS panel. So the integration of a DCS, FGS, and ESD is called ICSS, Integrated Control Safety System. So, so what are the major functions of functional requirements of a DCS? Basically, control, data acquisition, um, of course, giving alarm, logging the data, and importantly, all the historical trends. Of course, that is a separate machine, separate application, but all this data from the DCS will be used for the report generation. Then all the historical data can be stored. If you want to do some diagnosis or improve the security, this is where you need to go. So why do we have a DCS? Simply because a single point of failure will not disturb the whole plant, right? A particular controller or particular area, if it is faulty or needs to be replaced, we can just hot swap it and so on. So the redundancy is there. We can have multiple systems. So past trends can be monitored. Reliability, good speed, process information can be visualized by users in different format. On the HMIs, you'll be seeing that coming slides. Of course, these are expensive, and when these were designed originally, security was not. Security is still basically afterthought. So they are more prone to cybersecurity threats because these are again connected to some networks, and those networks could be exposed to internet or unsecured business networks and so on. So a regular upgrade and maintenance, and there are a lot of Windows-based applications, right? For example, there are no monitors here, but HMIs can be mounted on the panel, or sometimes the HMIs or the operator stations could be separate, so on. And there's a good chance that it could be end of life or obsolete and so on. So legacy systems has these problems. The upcoming present hardware, of course, there are still vulnerabilities here and there in the hardware, but they still have come a long way. OEMs are proactively taking steps, but it isn't enough. There's still a long way to go. So where does a DCS used? Power grids, oil and gas industry, chemical industry, water facilities, water wastewater treatment plants, any manufacturing. It depends upon the number of IOs. So DCS with a PLC, not going to take much time here. So basically DCS for a large process, right? PLC for a smaller plants. But what is happening is the line between them is kind of fading. The capability is what DCS can do, even the modern day PLCs can do, but it just gets expensive. You don't need $1 million PLC, right? You can do with 20,000 or 30,000, or maybe lesser cost PLC. So that's very briefly. Right. So we saw PLC, we saw DCS, and this is SCADA. So SCADA in itself stands for Supervisory Control and Data Acquisition, as the name indicates. So SCADA is not hardware in itself. It is basically a system which it's an application which supervises, acquires the data received from different locations. Like here you can see there are different distributed PLCs over various locations. Some are in the same network, some are remote, and The SCADA application is installed in this industrial grade hardware. There is a serial RS485 interface here. So the reason why we have PLC, DCS, and something called SCADA was uh, SCADA is something that is positioned on top of hardware to which it is integrated. So it will allow the operator to monitor the equipment status based on that the operator can control the process. So the operator sitting here can see all different locations, parameters, right? The parameters of the process from a single control room. And uh, especially when we have geographically distributed facilities over large areas, you cannot go and interconnect with LAN. And this is why the evolution of SCADA, right? Especially in electrical and not all industries, certain industries where where the devices or the hardware is geographically dispersed, like pipelines, uh, power transmission, water and sewage transportation, uh, railway networks, highways, subways. So these are the common industry sectors where such a kind of application to monitor and control large number of devices. So earlier, we used to have something called a telemetry and data acquisition system. They still are there. They still are used. Um, but SCADA has become more and more popular. So we'll see few more SCADA architectures. So if this was a certain way to get all the data, this is another. But it is in a same location, same network, but different areas of the plant. And you hear, so like I was saying, basically there are supervisory applications residing on the computers here, and you need a PLC or some kind of controller, right? Uh, the reason why SCADA started becoming more popular is these remote terminal units are basically just IOs, but now they also have some inbuilt controllers and almost equal to a PLC right now. With the modern day RTU is intelligent, but originally they were just dumb IOs where we give the IO, it goes to the SCADA system, and the control used to happen based on the application, the parameters. But PLC was originally where the control used to happen from different locations. The IO used to go and so on. So we have the supervisory computers, RTUs, PLCs, the whole communication infrastructure, and these engineering workstation, operator workstation. These are called human machine interfaces or HMIs that I was saying earlier. So this network connects both the RTUs and PLCs, and as I said, HMI presents the plant information, right? The SCADA drawings, or you might have seen the images. Maybe there's some HMI. So all the schematic representation of the plant is basically displayed, including the live parameters. So the HMI is linked to the SCADA and provides all the live data. This is another configuration of SCADA. Probably this is offshore here. This is another offshore facility where you have different instruments or equipments, and they are uh, an RTU with the PLC inbuilt in a wireless gateway. They communicate through radio and satellite, and they are linked with the LAN to see all the live data. So, what are the advantages of SCADA? Why are they so popular? It's easy to maintain. It would provide access to real-time data from a very far location, right? The corporate office is in, for example, in Delhi, and you have in southern India, you have this facility, right? So it makes a lot of things easier. So the implementation tools, the SCADA application or the other hardware, they are advanced, they are reliable, It helps continuous operation. Maintenance of equipment can be improved based on the feedback that is received. And of course, the process can be remotely monitored. So these are the advantages. What are the disadvantages? Of course, implementation of any system needs specialized skills. So that is that. And only when these data, live data are available, uh, the SCADA will work. So without this, having all the other hardware, it doesn't make sense. So importantly, the compatibility of this RTU PLC with the SCADA needs to be verified. So that needs to be checked. Not every equipment works with every equipment or the application. So again, application of SCADA or all the industries you already know. So coming to this slide, PLC and DCS versus SCADA. I'm not going to go into too much detail. Sometimes there is always a confusion. Like when you see all the details in a HMI. People equate HMI equal to SCADA. No, HMI is just a screen, just an interface for the human and the machine for all the live data. But the SCADA computer, this is SCADA primary database, secondary database. These are basically for redundancy. This is where the SCADA application lies. This is where all the processing happens. All the processing of all this data based on our requirements. The HMI here can be a separate application. This could be a separate application, a different make, model, and so on. So all this data that is crunched, analyzed, can be interpreted here using the representation. So when we talk about DCS, it's a process-oriented, process state-driven, while SCADA is data gathering-oriented, event-driven. So this is a very important distinction that you need to understand. So DCS will contain one or hundreds or more amount of controllers to implement the advanced process control, while SCADA systems cannot carry out advanced process control techniques. So again, the distinction nowadays is a fine thin line. With the technology being modernized, a lot has changed. The distinction between all these three still exists, but it's purely depending upon the application. So when we talk about PLC, it's a feedback control loop. It's directly controlled by the PLC. But when we talk about SCADA, the software monitors the overall performance of the loop. That's all. So DCS is a control device that has higher capabilities than PLC, as we saw. While SCADA is a software environment that can communicate with the PLCs and also at times with DCS also. It depends, right? Especially in the electrical industry, SCADA is integrated with controllers like DCS based on not to monitor the functionality of devices, perform data acquisition, data logging, and so on. Right. So I guess that gives you a bit of understanding about the differences. So this slide, probably I'm not going to speak much. It is self-explanatory. Like I said, these are certain distinctions, but if you're ready to spend, you can have a cheap DCS and expensive PLC. Ultimately, it depends upon the application, the ruggedness, the reliability, and the industry sector, right? So that is a major deciding factor. So probably once you see the recorded video, you can go in detail, or maybe you get the slides, you can go in detail and take a look. So moving on to the next slide. Right. So if you want a break, maybe once we complete this topic, maybe we can break. Right. So when should we use PLC, DCS, and SCADA? So like I said, application and industry sector specific. PLC is a controller, DCS is a controller plus network plus the software plus IO acquisition. SCADA is primarily a data collection plus system monitoring plus network and plus software. So this is a very simplified manner of saying. Of course, there are a host of other reasons and expenditure and various other variables that go in to decide, right? All right. So those three were the most important controllers that you need to know when we talk about cybersecurity, especially industrial cybersecurity. But there are some other hardware and devices that you still need to know. One is RTU. So this is a very simple one here, where you just have the IO module, and this is being transmitted using serial communications to PLC. This could be received by a radio or a LAN or something, and this is the basic structure. Of course, this module and this block diagram is different. Here you also have a CPU, a memory, and a power supply. Of course, this also has a power supply. But like I said, nowadays RTUs are becoming almost equivalent to a PLCs, right? Example for a small, this is a flow meter here. This is a flow meter, this is a flow computer. You have a wireless sensor node and an RTU here. And this looks like a solar panel. And this is a flow meter where it is connected to an RTU. So here you do not need an expensive PLC or a DCS, right? RTU with the memory and with a bit of computer processing actually works. So RTU stands for remote terminal unit. That's what RTU is. The main purpose of RTU is to monitor and control field devices inputs like valves, actuators, sensors, and so on. RTUs are essential components of supervisory acquisition data SCADA systems that we saw earlier, and these help to interface all the SCADA and the physical process by getting all the inputs data. This is RTU. So moving on, HMI or human machine interface is a user interface or a dashboard that basically connects a person to a machine or a system or a device, right? And nowadays, if you go to any hospital, X-ray machines or CT scans, or even a petrol bunk, there is some kind of display. ATM machine, there's an operator interface, HMI, with touch screens. That's the most simplest example. Almost every equipment nowadays has a HMI. This is in what we are seeing here is in the industrial context. The application, the criticality is at a different level, but HMI has become so ubiquitous that we don't even realize it is like ticketing kiosks, touchscreen kiosks for booking and so on. That's a good example. So what they do, they basically display the data, track various things, and we also have some reporting and so on. And basically, HMI is in a way similar to graphical user interface. Sorry, but it's like how you interact with the hardware to change the process or monitor the process. There's something called soft logic or soft button, right? Instead of hardware button, you can take control actions. It is not generally done, but for certain things, certain times, certain requirements, you also have an button on the HMI itself. It's called a soft button. You click on it, it works like a normal physical button. So what I was talking about was basic examples, right? Built into screens or machines or control panels and so on. Nowadays the tablets, industrial grade tablets, portable, they are becoming like a portable HMIs. So regardless of the format or which term you use to refer them, the purpose is to provide insight into the various progress or performance that is happening around the facility. So this is another slide talking about HMI. If you see here, this is HMI and various other controllers and devices and in the network are interfaced with the HMI. If you see the back pane of the HMI, unfortunately I don't have a photo, there will be various terminal blocks. It is not just a display, but there are some electronic modules. It may also have some memory storage. There are USB ports too, which of course is a security nightmare. You need to disable it or you need to put a hardware lock. But yeah, they are given for a reason, right? Like mouse or a keyboard or something like that, or a monitor sometimes. Again, for that you have a VGA or you have a different black box for that. But yeah. So these are this hardware is called speed drive. There's a variable speed drive. There is a variable frequency drive. They have the same concept, but the how they work are different. So here's a simple schematic in terms of how the speed of the motor to control the pump operation is controlled by the variable speed drive, right? Uh, there are direct methods to switch on a motor, but if you want to operate, like for example our airport conveyor belts, you don't want them running at 100 kilometers speed, right? You need a certain 2 kilometers or something, 2 meters per second probably, I don't know. There are certain requirements industry, like conveyor belts for logistics and so on. You need a smooth operation, right? And this is where a variable speed drive comes in. So like the famous Stuxnet attack, uh, of course it was a PLC program that was modified, but again the PLC gave command to a variable speed drive for operating the centrifuges. That is an interesting read. We'll be seeing at the case study tomorrow, but this is something that would be of interest to you. So that is speed drives. There are different control systems for different applications, right? That you can see on the screen. That are not as much common as you would know, but they are like building management system or a burner management system or a CTV surveillance systems. All these are some kind of hardware, some kind of software application, and IOs, inputs and outputs, either taking an action or doing a control or monitoring, right? So there are so many control systems out there. Yes, the important concepts will definitely feel boring because these are the basic concepts that you need to know, especially when you talk about an OT. If you do not know what the OT systems are, then how will you go and protect it? Uh, this is where the basic is. Probably, if you want to make it more interesting, probably you could give me some ideas to make it more interesting. Unfortunately, this is what it is. Probably these photographs might liven you up, make things more interesting. This is for a generator panel where we have a control panel, and this is a small HMI where you do the settings. These are analog meters, and this is an indication and so on. This is HMI, and this is a mimic panel where the status are displayed. This is an emergency stop button. Here, there's an analog. This is a selector switch. This again is a selector switch. So there are so many other different types of panel hardware that goes in to accommodate all these control systems. This is a PLC. So this is a PLC panel inside, and this is a PLC panel outside, where you have the HMI. This is a local panel, on panel HMI. There's always operator station on the table as well in the control room. Like if the operator wants to operate or maintain, then this is something that they can easily, right, because the control room will be very far from the this panel and so on. So for any emergency or sudden something they need to check a monitor, they can do that. And this is another panel. This is still two redundant. Redundant means there are two set of controllers instead of one. And SIL2 is the safety integrity level rating in terms of how reliable these systems can work without any downtime. This is for manufacturing industry, and this is for an oil gas. These are different make and models. There's a factory acceptance test that is happening here. Again, this is even the breakers, electrical panels, and there are small controllers, IEDs inside that monitors and so on. So we saw about the control systems, and these photographs actually show how they are in real life. Of course, panels, DCS panels can be much bigger. I don't think there was a panel photograph of a DCS, but yeah. So OT network architecture. All right. So we saw about what are the OT industry sectors. We saw about the field instruments. Then we saw about what are the various controllers. Now let's see how the architecture of the controllers are. You might have seen a bit earlier when we were discussing about the different controllers, but this gives a much more better perspective, like how the layout is. What you're seeing now here is a SCADA system layout, and this is how it is. Right, this is the control room where you have the HMI, you have the workstations, you have the data historians, you have the SCADA servers, and these are communication devices, gateways, and so on. This is just a general layout, and it could be through a LAN, fiber optic, or a radio or a satellite connection. This is a wide area network because it's a SCADA, and you have multiple field sites being connected. So here you see general configuration. Control center houses a control server, communication routers, and so on, and different workstations and so on. The control center collects the logs and information gathered by the field sites, displays the information to the HMI, and may generate actions based on the detected events. The control center also responsible for centralized alarming, trend analysis, and reporting. The field site is where the local control of the actuators and sensors so happens, and field sites are often equipped with a remote access capability. So remember this remote access capability when we talk about cybersecurity. This will be an important aspect. If we don't discuss this today, we'll probably discuss tomorrow. So originally, this remote access capability was allowed basically to help operators sitting in the control center to do some remote diagnostics or repairs or monitoring, right? Usually over a dial-up modem. Nowadays, we don't use dial-up modems. There are 4G modems available. There are secured way of doing a remote connection. But yes, there are still dial-up modems that are directly connected to the field sites without any security. And the communication protocols between here to here would be standard or proprietary protocols running on the serial and the network communications that are used to transport information from the control center to the field. Sorry. So what we saw was a general layout, but this is communication topology in terms of how they could be implemented. This is one among them. This is for a small facility where all the sites or all the locations are within a single location. It could be point to point, series star, multi drop, and so on. So basically, point to point functionally is the simplest type. However, it is expensive because individual channels need to be connected and configured, and the channel sharing has an impact of efficiency and complexity of the SCADA operations. Similarly, the series star and multi-drop configurations use one channel per device, results in decreased efficiency and increased system complexity because the number of channels again are increased. The next one, we'll see a large-scale communication topology. It is a combination. Basically, if you see here, it's a single site being connected to the SCADA server. Here, the same thing, if you group it into a master terminal unit or MTU or the main SCADA server, then it becomes a large scale. So large systems are basically hundreds of RTUs, often with the subcontrol server to unburden this main server, right? And the next one is a bit interesting. This is basically networked. Everything is networked. It's not radio or wireless. Here, this is something that, especially the current power grids or a substation or distributed electrical resources, this is how will be connected. It is a basically example of an implementation. So this particular SCADA system consists of a primary control center here and different point-to-point connections, which are basically used for all control of the field site communications. With there are two radio and one over a wide area network. With this could be a fiber optic cable as well. So basically, this is a regional control center, and through a wide area network, or could be an internet, which should be an internet, it's connected to the enterprise network. So what happens here is this enterprise network will be able to access all the control centers through the WAN and the field sites remotely for troubleshooting, maintenance, or for enterprise requirements. Again, these are all perfect examples of how insecure the current configuration is. This is how it used to be. Unfortunately, there are still a lot of sites almost the exact same configuration. So this implementation shows a SCADA network. Basically, this is for a railway sector where the rail control center is where the control room of the different sections of rail, right? And this could be on a single line at a different location. You have the relevant hardware to track the train and various other applications. So the SCADA system here holds the railway sections, different section 1, 2, 3 for status of the train, the signal systems, the traction, electrification, and all the other data. It doesn't have to be industrial data. It could be ticketing data as well, like basically from stations and so on. So this information is again fed to the operator over here. So the SCADA system monitors the inputs at the different centers and disperses all the information to the tail section components. So in addition, the SCADA system also monitors the condition of individual rail sections. So this is something very important. And based on the condition that is monitored, various commands like stopping a train or entering from like for example, there is a jam here, or there's a broken train shut down due to some issue, or if it is flooded, or there is another unscheduled train coming, anything can be tracked and monitored remotely from the rail control center. This is how it is at a basic level. There could be various enhancements based on the rail operator needs and requirements. And of course, the regulations and compliances also play an important role. So we have been speaking about SCADA for a while, and the reason why I wanted to share this important piece of information is mainly because uh, this is not something that is well known out of the industry, right? And ISA is, of course, the International Society of Automation. They also developed their own standard. So they are developing this SCADA architecture. We all know SCADA has been there for a while, and of lately, the requirements, especially the digital transformation, IIoT, edge, and cloud, the various additional requirements that are needed. And ISA 112 standard, their main aim is to develop the standards related to the SCADA um, to help develop the model and so on. So if you want, you can go to the site and take a look. Uh, Again, it follows a similar structure as the Purdue model. The reference model is over here. This is purely for understanding, but at level 0 and level 1, you have different requirements. This SCADA model will differ from the usual model that we follow for our control system, right? It's evident here because the need is different. You have field devices, sensor networks, local controllers, controller network. Then, because it being a SCADA, you have a wide area network. That is why it's called a backhaul networks here. It could be FO, or it could be radio, satellite, and so on. Then you have the communication requirements here, all the applications and so on. That is at this level. They still follow this same level, but the amount of uh, layers is basically increased, and you still have this here. So this is currently at the draft stage, is still not developed. Anyone can participate and join this standards committee. If you want to know more, do visit. So that was about SCADA. So coming to the DCS, we talked a lot about control systems, DCS control systems or distributed control systems. This is an implementation example that you're seeing here. You can see how it is used to control the production system within a single location, right? It could be a petrochemical or a refinery and so on, wastewater or power plant. These systems usually process control or discrete part of control process. So DCs are integrated as a control architecture. They are integrated, overseeing different level of controllers integrated as a subsystem, different subsystems. And DCS basically what it does is it follows a centralized supervisory control loop to mediate a group of localized controllers that share the overall task of carrying out the entire production process. Right? So it carries out the entire production process, one controller at a time for the whole plant. And the product and process control are usually achieved by deploying feedback or feed forward control loops. We did see about open loop and closed loop at a basic level. Of course, there are various other control methodologies like so different types of control loops are there. Basically, the reason is to accomplish desired product or process tolerance around a specific set point. Otherwise, it doesn't make sense to spend so much money doing some production. And they are more capable than PLCs. This we discussed earlier. They are tuned to provide a desired tolerance as well as self-correction. So that is also possible, especially when there's a process of upset. That happens a lot in the process industry. So this is how the production is modularized, right? There are different sections performing different actions, and this modularization helps to prevent or reduce the impact of a single fault. Like if there is a fault, this one goes down. It doesn't take the whole plant down. So that is a very important aspect. In many modern systems, the DCS also interfaced with the corporate enterprise network. And if you see here, um, this is basically a general configuration. This encompasses the entire facility and providing supervisory control, communicates to the subordinates via control network. So, yeah. And sometimes there is also a PLC available for various reasons, that control smaller processes instead of burdening everything on the DCS. It's a combination of DCS, distributed controllers, plus PLCs for certain processor applications. Again, these are purely application based, dependent. So another important aspect when we talk about DCS is the industrial networking that you of course see, how it is interfaced to different hardware and servers and systems. Uh, Most important aspect is the communication. So the industrial communication protocols like Modbus or Fieldbus are used, and it depends upon the hardware or the control system vendor and so on. Because Fieldbus and Modbus are open now, but originally they were, especially Modbus was a proprietary protocol. Then it was made open, and this is how general DCS implemented. And knowing this network topology, the network system architecture, the field level devices, the level 1 devices, level 2 devices, the level 2 applications, level 3 applications is very important as we go into cybersecurity. Because if you do not understand the OT processes or the hardware, you may not be able to secure it holistically. So that is the reason we are taking the time out and seeing through these boring slides. So what we saw here was centralized DCS with distributed controllers and the PLC. Here we are seeing a single PLC implemented for a specific process. So this is something that you saw there, a part of a DCS. But for a smaller facilities, um, based on the number of IOs, a PLC implementation is more than sufficient. For example, here we have an AC drive, there's a single field bus, and uh, then we have a servo drive here, proximity sensors, and this is again looks like not sure what exact application this photo eye is, but it could be a presence of some object or light detection or something like that. This looks like a conveyor belt here, and that's the reason why we have this light tower here, signifying it is in stop, it is in running, or amber is for about to run. So that is a part of safety requirement. Then we have HMI, we have a PLC, and all this PLC data. Of course, we have a data scene, and we have an engineering workstation to do any operations or design configure the engineering data. So PLCs are both used in both SCADA and DCS systems as a control components of overall hierarchical system. In case of SCADA system, they may provide same functionality for RTOs, but it depends case to case basis. But when we talk about DCS, PLCs are implemented as a local controllers within a supervisory control scheme. So in addition to PLC usage in SCADA and DCS, PLC are also implemented as a primary controller in smaller control system, where the configurations to provide operation control of smaller processes. Uh, for example, here, uh, like I told, it was an assembly line, right? That could be multiple assembly line, and the topologies of the network architecture differ when we compare with the SCADA or the DCS. The reason being, there is no central control server, and of course a HMI, right? And therefore, primarily they provide closed loop control without any direct human involvement. In the sense, if there is anything going wrong, of course, the person seeing the engineering workstation will immediately come, or there could be some kind of uh, stop, then this light would probably blinking. So this simple architecture shows a simple manufacturing process being performed by a PLC over a field work. And this PLC is accessible via engineering workstation for programming changes and so on. Right? Like if there are some parameters of different products are being produced in this assembly, then the settings might need to be changed, and that can be only done by an engineering workstation. So this engineering workstation normally doesn't have any access to other networks. It can be accessed only at site, but yes, it can be configured to be accessible remotely, but normally for an engineering workstation it is avoided. uh, in that case, we can have an operator workstation here, and the operator workstation can be remotely used for access for monitoring only, not for controlling. Right. So that was about different network architectures that we see in the OT industry. All right, let's go. Okay, so we saw about various aspects, and coming to the very important aspects. Uh, the there is a reason why I'm emphasizing on all these aspects, right? Normally, when there's a cybersecurity training, especially on OT, people directly get into the cybersecurity part of it, but it doesn't give a 360-degree view or understanding of the processes. This is a short training, so I cannot be very comprehensive. So I've tried to condense the important topics and concepts one needs to know. One doesn't have to be specialized in it, but at least if you guys are aware, it'll be very helpful. Right. So let us go into the next topic: OT communication protocols. So we all know about this OSI model, right? And OSI model, open source interconnect, which has the 7 layers. This again plays a very important part in the industrial communication protocols that we are going to see. So, if you guys are an IT expert or OT expert in terms of cybersecurity or whatever role you guys do, this is something that is very important, because in whatever role you do, if you know about the OSI layer, and if you know about OSI layer, then you can easily deconstruct the industrial protocols, right? Whether it is proprietary or whether it is open, you can still understand the frame, you can decode it, and you can see if there are some errors or malicious data, right? So it's very important to know this OSI layers, 7 layers. So when we talk about an industrial control system, OT system, uh, all the information data communications is done through using the protocols. Some are designed for specific application, depending upon the industry. Like for example, automotive, we follow CAN bus. If it is building automation systems or building control management, we follow BACnet. If it is oil and gas, petrochemical, or petroleum industry, we follow Modbus, Ethernet IP, and so on, Profibus, Fieldbus, and so on. So in general, in OT systems or industrial control systems, it is first necessary to transmit the data between the sensors and the actuators, right? The podium module that you might have seen again and again, between the level 0. Level 0 to level 1 is usually analog or a digital signal, depends. But there are smart devices like field bus configurations and so on, where they work on the field bus protocols. But if it's an analog, then level 0 to level 1 is doesn't need any protocols. But usually from level 1 to level 2 and so on, these protocols are needed for various systems. So very important aspect is the transmission distance that can vary from few hundred meters to few meters or maybe more than that. And the transmission can be uh, even carried out over a much greater distance based on telemetry technologies or optical fiber cables and so on. So at the moment, we'll just limit to Modbus, Profibus, and few other protocols, right? Prior to all these intelligent communication protocols, RS-232 or RS-485 or a radio link was the common transmission mode, right? And see, it can also be carried out by an electrical signal till a PLC or a DCS without using any computer protocol. But there are certain challenges, the complexities of maintaining. If it is for just a five number of IOs, it is okay. But if there are 1,000 or 10,000 IOs, that doesn't make sense. The maintenance is a headache, the troubleshooting is a headache, the complexities increase, and it doesn't warrant the cost, right? So that is where because of the reliability requirements and other reasons, the communication protocols started becoming more and more prevalent. Remember, these were still 15, 20 years back. And we are going to just talk about how the protocols works, what are the protocols, and if it is secure or not. At that time, security was not part of design, right? Because inherently systems were trusted, and safety was the only aspect that was taken care of. So, like I was saying, at higher levels, especially level 1 and level 2, it is necessary to transmit information between the various processing units like PLC, RTU, and the supervisory control system and so on. So, different types of protocols are Modbus, Profinet, Ethernet IP, OPC, UA, Unified Architecture, that's more recent. And this data transmission is usually carried out by Ethernet. And in 90s is where the proliferation of the commercially available off-the-shelf IT hardware and cables started becoming more prevalent. Because the cost was reduced, it was easily available. Uh, Windows OS computers being used instead of embedded devices, and Ethernet communication kind of became a default. And they were traditionally based on the computer protocols such as Ethernet or Wi-Fi or TCP/IP. Wi-Fi did come later, but Ethernet and TCP/IP. So since 1990s, there has been a convergence of protocol. First, Ethernet 802.3. Some of you might have heard, right? And those days, especially where the real-time aspects are not that critical, use IP, which also allowed the use of Wi-Fi equipment. The IP network equipment is ubiquitous because it's easy to deploy, relatively inexpensive, and well-known to administrator. So what happened was the connection of manufacturing systems with the company's IT systems or the production management becomes much easier and better. So you should understand that this convergence is not limited to ICS, but all the other aspects of enterprise requirements like television, video surveillance, VoIP, and many other things that use IP networks. So By now, you should realize that this is the reason why there is a significant increase in companies' vulnerability to cyber attacks. I hope you get that. Right. So now to the first protocol that we're going to take a look is the Modbus. Uh, and if you uh, see or compare with the 7 layers over here, and these are different configurations actually. So this is Modbus on TCP, and this is for RS-232, RS-485. RS-232 only two devices, the master and slave, can communicate. When you have RS-485, you can have multiple slaves, multiple devices that you can connect. But again, they were serial communication. This as well. This didn't take off that much, but there are certain applications. So Modbus is one of the oldest industrial control protocols that was developed by Modicon, and over time it was made open. It grew. Once it was open, even before it was open, like especially the serial type communication was used 1980s to 1990s. It grew considerably. Then, in order to integrate with the modern systems, especially the TCP/IP networks of the IT that we have, this Modbus over TCP was developed. This happened in somewhere in late 90s or early 2000s. And at present, it is one of the most widely used protocol in many different types of industries, especially critical infrastructure. So this is something that if you want to be a penetration tester, or if you want to work with embedded device testing, especially industrial control hardware, then you need to know how Modbus works. What are the different frames, what are the different layers, how the data is encapsulated and transmitted, and so on. So let's look about three types of Modbus implementation. One is serial Modbus using RS-232 or RS-485 in RTU or ASCII version, where the bytes are encoded on 2 hexadecimal characters using a variety of physical means of transmission like cables, fiber, radio, and so on. Modbus Plus over HDLC, where HDLC stands for High Level Data Link Control, uses a high speed token passing network. And Modbus over TCP/IP, the most popular one for over the Ethernet. So these are the three. So generally, the TCP/IP version is used between the levels 1 and 2. That is between the PLCs and the various supervisory computers, whereas RTU version is used between levels 0 and 1 to connect PLCs to IEDs or intelligent electronic devices, especially in the electrical or the power industry, to the PLCs. And even those are slowly, the trend is towards a generalization of TCP/IP even at the lowest levels. Like I was saying, level 0 to level 1 also TCP/IP is being used. So this Modbus protocol is so common in majority of the implementation. It's a master slave protocol. Some of you folks here might already know, but the reason why I'm talking about this again here is so that we are seeing a different mix of crowds, right? So I wanted to take some polls, but maybe tomorrow's session, I'll try to understand the mix of the people so that I can answer your, because tomorrow will be all about OT cybersecurity and various aspects. So coming back to the protocol here, the master control is the communication and the slave responds to the request. So the protocol is very simple. There is no procedure to connect to the network, no detection of maximum response time, or no diagnosis of the slave status. So the basic functions essentially allow the words to be read or written from the slave's memory, and the frames contain a function code and associated data. Now you can understand why it is not secure. But yes, there are secure implementations of Modbus also available. At the moment, I'm not discussing that for the simple reason because it'll just make it more complicated and lack of time as well. So just giving a basic overview of the different protocols and some information about how they work and what they are. All right, so that was about Modbus. Let's take a look on. So Profibus is abbreviated as Process Field Bus. It's a field bus communication standard, originally promoted by the Germany and mainly Siemens. Um, it originally started as serial communication by cable RS-485 and also on optical fiber. It is a master slave protocol similar to Modbus, but it is a bit more sophisticated with the procedure to join the network and time validations. These are very important aspects, right? Like in manufacturing or other industries, you have certain requirements, especially time sensitive, critical, and deterministic aspects, especially when you're dealing with real time data. So, this helps a lot. So Profibus is a field bus mainly designed to connect with field devices to the PLC, and comparatively, it's not vulnerable to attacks via TCP/IP. So it's a standard that adopts Ethernet as a physical interface for connections rather than RS-485, and it has a token-based reputation system to provide uh, real-time functionality. So, modifying the protocol over a fraction of time with a given periodicity. With the remainder of the period, basically, what happens is it operates in the uh, conventional 802.3 Ethernet. So, the good thing here is Profinet basically offers full TCP/IP functionality for data transmission, which allows applications to use it with a wireless network and high speed transfers. So that's the best part. And equipment using Profinet is usually, uh, especially time sensitive or time critical, where the reliability is very important and you need real time data to take control actions and so on. So this is a very simple architecture of how Profinet is, and Profinet does not have any native security features inbuilt. Uh, the thing is, the functionalities incorporated in the protocol in itself focus on improving the availability and operational reliability. So, in order to prevent a potential attack on a Profinet network, uh, we need to do a segmentation of networks, as in virtual LANs, or bring in demilitarized zones or DMZ layer. So that's briefly about the Profinet. So this again is commonly used as well. Like I said, Profibus, Profinet, and they were invented by Siemens and through the German Industry Association. So when we talk about specific vendors devices like Siemens, they predominantly have this protocols in all their hardware. Of course, there are other smaller vendors too, but yeah. So DNP3 and IEC 60870 is a protocol that is developed in early 90s, and it is mainly used in the electric sector or the power sector in United States and Canada. It is not used anywhere else in the world, at least as far as I know, and it is very rarely used in the Europe. In the very beginning, they used to use DNP3, but for various reasons, they slowly shifted to um, other alternatives like 60870 and so on. So these are different versions. There are different versions of it actually. So it is a three-layer protocol operating at a data link application and transport layers, as you can see here. And the original DNP3 didn't have this encryption authentication. It was later when security and authentication requirements of the data is being transferred were needed, this was developed. But originally, this protocol was designed to maximize system availability with less emphasis on confidentiality and data integrity factors. So, at a data link level, some functions are included for detecting the transmission errors by calculating the cycle redundancy check. So, this is something that we all know. So, there is no additional security measures to the Ethernet protocol at that level. So at the application level, a variant of DNP3 adds the possibility of authentication, and this kind of solves several security problems. It especially prevents identity theft and message modification by malicious actors. So here, I didn't. I should have probably added a separate, more detailed slide about 61850 with 62351. This is a security protocol. So 61850, this is predominantly used worldwide, even in India as well, especially in the power sector for information transmission and so on. 61850 also is known for its unsecure aspects. So that's where this IEC 62351 was developed. And this goes, when you implement 61850 with 62351, it goes a long way in improving the security aspects. So these are the two main protocols that you need to know, especially when you're talking about the power sector. DNP3 more respect to the North American and Canada and US, but globally, if you're working in the power sector, power transmission, power grids, distribution, and so on, or you're working with digital substations and so on, 61850 is something that you need to know, especially the inner workings, how the data is encapsulated and transmitted, received, and so on, and how 62351 actually helps it to make more secure. It'll help you in terms of, especially when you could be designing, or you could be doing some testing or validating the functionality during the cybersecurity testing, or during the factory acceptance testing, right? So especially when you're checking a functionality of hardware, ultimately, apart from all the various aspects of the operator station using the OS or the firewall switches and so on, communication protocols are another important aspect, right? So there are some test cases, test instructions that can be tested that it is working in the intended way and so on. So it is really good for you folks to know, especially if you're in the power sector. So coming back to protocols, another important aspect that again is used in the industry is Ethernet IP and Common Industrial Protocol. The reason why both are together is almost same, and this CIP, or the Common Industrial Protocol, was developed by the Open Device Vendor Association to automate the industrial processes. So CIP basically includes a set of services and a message for control, security, synchronization, and also helps in configuration, the information that is being transmitted and so on. This can be integrated to the Ethernet networks and the internet. So what happened is a number of CIP adaptations came in, providing interconnection and integration between different types of networks. So one of the adaptation is Ethernet over IP. which is an adaptation of Common Industrial Protocol over TCP/IP. So, yeah, there's another adaptation is control net. The only difference is CIP is integrated into a concurrent time domain multiple access, which actually allows the deterministic time communications for critical real-time applications. These are very specific applications or use cases, right? And this may not be very common across the industries, but if you have a use case and this works for you, then that's the reason why this exists. Then, of course, another prevalent adaptation from CIP is DeviceNet. Basically, it is a CIP adaptation with a CAN controller, and so we have been talking about CIP and CIP adaptation. So the CIP is a protocol based on object-oriented modeling, right? And each object consists of attributes, could be data, services, commands, connections, and behavior. So what happens is the relationship between and the data and services, that is the behaviors. So this is very helpful and very important as well. So this kind of enables the CIP protocol to offer a wide range of objects to cover over typical communications and functions with common elements in automation process, such as input or output devices, whether analog or digital, um, HMIs, motion controls, right? And uh, because of this, what happens is, especially earlier, when we are talking about different industry sectors, we were speaking about batch processing, continuous operations, and discrete manufacturing. So SIP as a protocol makes a lot of sense to be used in discrete manufacturing. And the notion of the profile actually makes it possible to define if the common communication object is implemented in a piece of equipment, and this communication is based on the producer consumer model, which can be a single or a multicast. So in first case we are talking about explicit messages, and in second case we are talking about implicit messages. So although CIP uses a formalized model, it does not define any mechanism as in implicit or explicit for security. In addition, what it also does is it defines objects required to identify devices, which actually can facilitate the discovery of equipment in the network and provide targets for attackers. So, since there are also common application objects for exchanging information between devices, right? The intruder actually can be able to manipulate a wide range of industrial devices using this type of object. So these are some of the challenges, especially when you implement SIP. So in addition, the characteristic of some SIP protocol messages, especially real-time multicast, are incompatible with communication encryption. So the SIP does not provide the mechanism to do that. Right. So we were talking about the SSIP protocol. Ethernet IP defines two connection methods using TCP/IP. Explicit messages using TCP and implicit messages using UDP. Ethernet IP actually is much more commonly used, as far as I've seen, in some of the industry sectors. So it is again good to know the implementation of a Ethernet IP protocol. And when we talk about explicit messages, they follow the client server or request response connection model. I mean, so what happens is the PLCs and HMIs, right, which you saw, So the diagnostic messages and file transfer happens. And the commonly used ports are TCP port and UDP port. TCP port, it comes under 44,000 something series, and UDP port comes under 22,000 something series. So it's yeah, it is something I didn't remember recollect immediately. So although Ethernet IP is more modern compared to protocols like Modbus, it still has the security issues that leave us vulnerable, right? And this is being used across multiple industries as well. So this makes it much more important to learn about this protocol and how to mitigate that. So we're not going to see just few more protocols before we go to the other topic. But this is something that you should know. This is not a protocol in itself. OPC has evolved into the current OPC UA or unified architecture that is more modern, and that is something that um, various disparate systems or different vendors can interface and communicate together. It makes a lot of things easier for both the vendors and especially importantly the asset owners. So understanding the OPC and the latest OPC UA protocol makes a lot of sense, especially if you're working in the OT industry or your IT person in the OT industry, or if you're OT cybersecurity engineer. Um, OPC UA is inherently secure, and compared to the previous OPC, which is a nightmare, and it also provides a lot of interoperability. That's the reason why people are using OPC, right? Because uh, two different vendors might use Modbus or use Profibus, but still they are not able to talk to each other. You still would need a gateway device for that, unfortunately. So that is how it is. So like I was saying, OPC UA provides a greater security to the architecture. So it is uh, advisable to deploy OPC UA rather than the traditional version of OPC, which is a nightmare. And before we go on to the next topic, I wanted to also talk about CAN, which is being predominantly used in automotive sector, right? And CAN stands for Controller Area Network. This was originally developed by BOSC, and it has become its own standard. Actually, there is a specific ISO standard that describes this in terms of how the format is and so on. So it partially defines the service for layers 1 and layer 2 of the OSI model. So how does a CAN work? So CAN transmissions operate on the producer consumer model again. So when the data is transmitted by a CAN device, it concerns another device that is designated by an identifier, um, and this identifier, which must be unique on the network, also provides the priority of the message. So what happens is all other CAN devices listen to the sender and only accept messages that is relevant to them. And this protocol is a serial type protocol. CAN protocol frame basically consists of identification field and the data field. Identification field and the data field. And plus various requirements for synchronization, acknowledgement, and verification. So, as I said, it is widely used in automotive world, and most of the models currently produced actually use it. Maybe you can go check your car if you want to try hack your car. You can do that, but at your own risk. Of course, you shouldn't do that. Maybe in a lab or a home lab you can set up, and these devices are very economical comparatively to other devices, so you can play with them. That would be my suggestion. And I don't know if you folks remember, sometime back, maybe 7 8 years back, Um there was some famous attacks on the Jeep models of that time. So there was a research paper at that time, and if this is something of interest, you should probably read that paper. So, like all protocols before that we saw, again, this is also unsecure, unfortunately. So that come so with the canvas comes to the end of the industrial communication protocols. So the next one is the next topic would be IT versus OT, which again probably would be interesting. Sorry, would be interesting to many of you folks, because this is where we slowly start the cybersecurity journey. So far, we were talking about uh, the OT ecosystem, right? Now we are coming to the security aspect. So before we can go into the cybersecurity, especially the OT cybersecurity, let's take a look about OT versus IT. If you look at this table, um, at a basic level, you can see the various differences, right? And these are categorized into different categories like performance requirements, availability, reliability, risk management, system operation, resource constraints. And in the next slide, there is communications, change management, um, managed support, component lifetime, components location. So these are the key categories that you need to understand the difference, especially when we talk about IT or information security, information technology system versus an industrial control system. So while the information on the table, you can take a look. I'll share something from my understanding. Um, that of course, if I try to put in the slides, it will be too much space. So while you take a look and read this, I'll try to complete what I want to share, and then maybe we can go line by line. So the important difference when we talk about IT versus OT is the device or the software or the system lifetimes, right? Um, varies. When we talk about ICS, it sometimes goes to 15 to 20 years, and um, when we talk about the design and the objectives, uh, OT always focus on safety, reliability, functionality, but not for security, at least the cyber security. But that is something that we want to change, right? It is not there, but that's something that we need to. And that is our aim also. How do we repurpose the IT cybersecurity concepts for the OT? And OT is always about proprietary software, hardware components, and different communication protocols. Interoperability is always a challenge. It doesn't work smoothly like how things happen in IT. So there is always a challenge, especially if you're new or if you do not know, right? Especially for IT people working in OT, they're scratching heads. There's nobody to guide. The engineers or automation OT engineers are always busy with some troubleshooting and so on. And there are a lot of legacy systems. IT like updates like year on year, not 100%, but it's fast. At least in 3 to 5 years or 10 years, there's a sea change in how IT or information systems evolve, but not OT. And one of the challenges that someone was asking, like, how do you manage the updates or the patches, right? The firmware and so on. So the software and component or the hardware updates can be very, very tricky because they need to be managed correctly, and it needs to be implemented when without disrupting the systems, right? Like you don't shut down to do a patching or an update, or if there is a uh, or if there is a unscheduled shutdown, you don't go and implement the patch because that might backfire on you, right? And there are not tools available to make this task easier also. Of course, last 3 to 5 years there's a lot of solutions, third party solutions that has come up. But again, um, they just make the process easier, but again, taking the decision is subjective and based upon the individual organization. um, because not everything can be patched due to compatibility or the issues and the platform, obsolescence and so on. So we need to know if the patch is critical, or what is the priority, if it is high priority, medium priority, or a low priority. If it's a high priority, you should do within a week. It's a medium priority within 3 months. If it is a low priority and if it doesn't affect, probably not. So this is how it's generally categorized within the OT industry. But company to company, industry to industry, country to country, things are not the same. They have their own practice based on the guidelines and best practices. So when we talk about operational procedures, especially in an OT environment, we don't patch it every Tuesdays of the month whenever we have a patch from Microsoft, and not as rebooting a system that doesn't work as expected help, right? Because there is a because every downtime needs to be scheduled. So you can only patch during certain periods of downtime whenever the bigger or the heavier equipments need to be maintained, and this happens uh, by yearly or annually or once in 3 years, depending upon the type of equipment that we are talking about. And in different types of industry have their own uh, downtime schedules as well. It's called a turnaround and so on. And another important challenge is vulnerability management. It gets more difficult, right? Because there are so many third party applications, or layers, and sometimes you have a OS like Windows 7 or servers like 2008, where the patches are rolled into a single bundle, and what it becomes is it's very complicated. It actually increases the risks. And for OT, the focus is always on the field instruments, the safe operation, uptime, the trust in the process control data. These are the primary drivers for folks who work in the OT. This is primarily different than in IT because the focus is predominantly on the security and confidentiality of the data, such as client records or banking information and so on, or could be the devices used in the corporate network like your workstations, laptops, and so on. While IT security is also important, OT cybersecurity also is equally important. There are totally different contexts. And yes, when we talk about OT, unfortunately, legacy systems do exist. And for certain systems, there may not be any remediation or a different process or procedure because these devices and the systems, when they were implemented, were insecure by design. It's not because they wanted to do that, because at that time the focus was simpler communications and so on. Security was not even an afterthought because uh, back then trust was not an issue. Everything was trusted. Now it is zero trust. That's the unfortunate sad reality. And many times vulnerabilities may not be publicly known or reported, or asset owners may be basically unaware. That's another unfortunate situation. And it's not a blame game. Okay, the responsibility lies with the vendors or the OEMs or the system integrators. Everybody needs to work together. So that is a huge challenge, right? Like people nowadays give advisories. There are certain bodies which give advisories, but it needs to reach to the relevant asset owner, and or the concerned person within the organization to take a call. Sometimes things might fall into the cracks, so they are one of the biggest challenges actually. For a bigger organization, they might have a well-established team, they might have various resource availability, but that's not the same for all, right? Like normally, cybersecurity teams, especially OT, may not be existent. IT people are responsible for that as well. So it just increases the complexity. They may not be unaware. And another factor is compliance and legislation, right? Uh, Normally, that is the driving factor also, actually. And uh, because all the budget that is there is usually focused on that. So sometimes it can be a good thing, but what happens is, uh, if you do certain changes, especially in pharmaceutical or food and beverage industry, where due to regulatory and compliance requirements, if you even change a small variable or aspect, you need to recertify the whole system. And they may take a call, let okay, there is the cost for recertification does not make the business objective, because it simply outweighs or the security updates, so they are neglected. Or it may happen that you need additional compensating controls, countermeasures that might be more challenging, so the cost with respect to the risk might be much higher, so they are ready to take the risk. Well, these are some of the important aspects. One very neglected, and one of the reasons because there is so much demand for OT cybersecurity professionals is skill and resource shortage, even within the IIT. Then, if we talk about OT cybersecurity, it's almost the demand is like everybody wants so many people, qualified people, so many knowledge people, but there aren't. And one of the reasons why we are having this masterclass is to, at least even if we cannot do 100% knowledge transfer, at least whatever is possible, right? And that's why we are here trying to do that, spending our personal time and effort trying to make people more knowledgeable about all these things. And this is also one of the reasons for this situation, as organization normally rely on more experienced people and a legacy system. All these skills were previously that were there in those in that time period not being translated, and the young people not being given opportunities to develop their skills, grow into the roles, and so on. So that is one important aspect. Then when we talk about removing access controls or changing credentials, it's very challenging in industrial environment because of the design of the systems and how they are set up. So sometimes when people exit out of the organization, the credentials still might be there. And at times what happens is, you might have this access, instead of a role based access control, you might have the credentials for variety of functions, not limited by your job function. That is another challenge. So some cybersecurity systems require a period where visibility and operation is lost while credentials are changed and system is restarted, right? So this may not be a major factor, but still it is one of the aspects. So these are some of the differences between IT and OT, in addition to whatever is listed. And these side to side, company to company, um, not maybe all of them not may not be true, but at least at varied levels. It might apply to certain sites and certain asset owners who they are responsible for. So, hope while you are listening to me speak, you took a look and have a good understanding, right? Like, I don't think I need to go line by line because this is something very common. Um, but unfortunate reality is, even if it is common, people do not know these things. These are quite basic, but that's a sad reality. So these are the some other categories that you need to understand how IT versus OT systems work. And if I want to summarize the cybersecurity, especially IT versus OT, the operational risk difference between ICS and OT systems create the need for increased sophistication in applying the cybersecurity when we talk about operational systems or the OT systems. This is the reason why we need a cross-functional team of control engineers, control system operators, automation engineers, and IT security professionals to work closely together to understand what are the implications, especially during the installation, operation, and maintenance of the various security solutions, not just patches, in conjunction with the control system operation, right? And when IT people, IT professionals working with OT, ICS professionals need to understand the reliability impacts of IT technologies before deployment. This is important because some of the OS and applications running on ICS OT systems may not operate correctly, especially when you talk about commercial off the shelf solutions, because of the way OT systems architectures are architected, right? So we are talking about the various differences, the categories, and so on. So there is this one pager document that I found, and this is a good work, right? Like, uh, we always talk about the obsolescence and the speed and the commercial of the self and so on. But when we talk about IT versus OT, it is the mindset, the technology, and the requirements that you need to have in mind. And this is a one page document. It may not be comprehensive, it may not cover everything, but these are the key aspects that one needs to know. And this is a very good compilation. So we all know IT moves data and OT moves physics. So the individual differences are mentioned here, but what we need to understand, because of these differences for the operation environment, for the technology, for the design mindset, life cycle, and the dynamic nature, the way which IT and OT evolves, upgrades, and so on, the priority in operation with respect to the security objectives, another challenge of regulation compliance, all this translates to the impact for OT here: lower performance, fragility, vendor dependence, insecure by design. I don't like this term insecure by design. It is not intentional, because back then there are different requirements. Now we know there are certain issues, certain things that we need to take care, and people are doing that. But still, we still have a long way to go. But again, the challenge is how we use the IT concepts, especially the OT vendors core skills and the operator personals, and develop the competency. So this is something very important. And what is the strategy that we need to implement? How do we ensure that we do all that and focus on the reliability? And ultimately, for any business, any organization, any industry, this is very important: the public interest, the environmental impact, the life safety, and so on. So it is not only commercial interest, but the various safety aspects also needs to be taken care. So we in the ICS OT community are actually tired of explaining the IT versus OT. It's not because we don't want to. Of course, people who do not know, we always welcome and share and explain the challenges, the complexities. But what happened is, in any of the conference, if you attend, people have stopped about speaking about this topic, because every now and then, almost there's someone who speaks on that, right? Because we have evolved, there are other things that we need to take care. And as we can see, these differences are significant, which has important security ramifications and consequences. The impacts of the risk are different, as well as what causes them. The operating constraints are different. The staff in charge, be it IT or OT, come with different cultural mindsets and have different skills. So when we talk about cybersecurity or security management within the organization for the respective systems, we need to take all this into account, the various aspects of this that we discussed today. So if you want to know further, probably you can take a look here. This is something interesting. Whatever is mentioned in these two are basically covered in the one pager that was shared in the previous slide, and this is something that you can take a look. This is a very interesting article, and this was the source for the one pager as well. It's because previously to that, everybody had their own version of IT versus OT, and it was not uniform. But the aim of this one pager previous slide is to share the information within one slide without being too boring. So this is a difference between IT versus OT systems. Now we are going to speak about the final topic of the day, introduction to ICS OT cybersecurity. This will be again at a very introductory level, because after this we are going to get into groove, and tomorrow's agenda will be power packed and hopefully very important for everyone who is interested to know about OT cybersecurity. So this image that you see here, from the 2000s till 2018, 2019, but after that we had this colonial pipeline, but that was more of an IT event, but it did impact indirectly to the control systems, but we're not directly. You get a sense of an idea, like how much things have changed, right? Like there has always been events happening, but it was not reported. At least these were at a major level. Certain cases we'll be taking a look tomorrow, especially the Stuxnet, the Ukraine power grid, and so on. Trisis was another major attack as well. This is something that is important. That so we'll be deconstructing the attacks, and we'll have certain categories that we'll take a look. So how has this OT cybersecurity evolved? This is one image I took from this Sinclair blog. So he's one of my mentors and my good friend. So he says that over a period of time, the OT cybersecurity has evolved, but there's still a long way to go for sure. The technical security, which was almost non-existent, has increased. The awareness over a period of time. Now there is sudden interest. There are opportunities to address them, develop resources, train ourselves. Then we have various guidelines, good practices, standardization that has happened. Risk management concepts, especially when we talk about OT cybersecurity, like IT, we have in IT we have ISO 27000 series of standards, frameworks. NIST also has a cybersecurity framework. Then we have information security management systems for auditing and so on. So of course, IoT cybersecurity is not bit comparatively straightforward. So one of the ways to assess the risk, understand the risk uh, posture of an organization. We have a risk management methodology, which I'll be touching upon tomorrow as well. And overall, the attitude and the mindset, the culture has also comparatively evolved. That is probably last 5 years, because of the so many ransomware attacks that used to be on IT systems are happening on the industrial systems nowadays. There are some devastating attacks that we'll be discussing tomorrow. So whole lot has changed. So as my good friend Sinclair says, OT cybersecurity is not a single system that you deal with. It's a system of systems. It's a blend of process engineering, process automation, risk analysis, and information systems and cybersecurity all together combined. So even though this IT cybersecurity techniques, best practices, tools, and strategies overlap with IoT, um, attacks within IT are basically broken down into three categories: confidentiality, integrity, and availability. CIA, these three terms is what we refer to as CIA triad and are tightly coupled to data, which when we take a look at OT, the priorities are totally different when we observe it. And especially all this OT systems, industrial facilities, and critical infrastructure operations, the premise is safety, reliability, productivity. It doesn't mean that CIE or AIC or whatever, like, of course, in OT cybersecurity, based on the standards and certain guidelines, we have something called AIC, it is called availability, integrity, and confidentiality. Confidentiality requirement is very rare, but availability and integrity is the most important aspect. The reason why safety wasn't latched on to the terminology is safety by itself already existed, and I'll tell you why. What happened was, when uh, there's a certain process or a methodology for developing the industries, right? You have some conceptual model, then you do a basic engineering, then you do a detail engineering, then you do some inspections, pre-commissioning, commissioning, then operation. During operation, what happened is, like IT OT industries also evolved over a period of times. Certain incidents and explosions and various events that happened over a period of time. These happened due to bad design, bad operation, hazards, some things we might not have thought through during the design process, human errors. There could be n number of aspects, right? And for the very reasons, because of, even though you design based on certain requirements, there could be some kind of errors that creep in, right? um, if the design is not checked, or sometimes it could be double checked, but sometimes people miss to see certain things. I don't remember this exact thing, but there was rocket technology that was being developed by US and European partners, and they got their units wrong. I don't remember the exact thing incident, but only when they did the root cause analysis, they figured out that nobody had bothered to check what units they were using and what units the other team was using. So inadvertently, certain errors, mistakes can creep in, right? And it makes the system unsafe, or you cannot expect the human to uh, manage all these facilities by themselves. Humans are humans, they also prone to mistakes, operational mistakes. That's why we have standard operational procedures. But doing too many manual things also, it's not impossible for humans. That's where we brought in certain um safety systems within the design, and hence the reason we have emergency shutdown systems, fire and gas systems, and many other such safety critical systems, which are part of the OT systems, but I'm not sure if the architectures, but maybe tomorrow we'll briefly start with the network architectures before we go into the case studies, where I'll show you the different safety systems and so on. Normally it is air gapped, but again, it could be linked by physical hardware rather than communication protocol like Modbus or Fieldbus and so on. They are still maintained independently. They have much higher reliability in terms of operation, because in certain conditions they need to shut down, open or close, or fail safe, right? Failing safely. So failing safely, it could be open the valve, close the valve, whatever that could be. And these are the reasons why, because of the safety aspects, certain safety systems were built in. So hence safety happened to, based on all these incidents, safety standards. There are certain standards also that parallel developed. That is something called IEC 61508. It's a general functional safety standard. IEC 511 is for oil and gas functional safety. Then for automotive industry, we have a functional safety. For oil and gas and automotive, is totally different. But the ultimate inherent thing is designing some safety within the thing. So security at that time was not a requirement, because everything was trusted, but now it is not. So as these systems evolve, the pace and progress of security then has several constraints that is not seen in IT or enterprise environments. So I wanted to put some very interesting picture here, but I couldn't get it. But what is the current situation with respect to cybersecurity? What are the trends? So, so cybersecurity is it's a popularly used term, right, for protection of computer and communication systems from electronic attack. Sometimes it's also referred as information security, which is a mature discipline. It's a known fact, and it is evolving rapidly to address the various changing threats. It's known by everyone. Although they are also applied to computers and networks used for information processing and business requirements, they recently have been started to apply on the industrial systems as we know it. But these systems are a combination of personal hardware and software that can basically affect or influence the safe and secure and reliable operation of an industrial process. So what is happening is, because of this shift of applying the IT standards to the OT systems, that this has resulted in a creation of something of a hybrid discipline, bringing together elements of cybersecurity, process automation, and process safety. This combination is referred to as industrial system cybersecurity. So, OT cybersecurity is not one dimensional. There are certain other things that go along with it: process automation, process safety, functional safety. These parallel, these terminologies that I'm saying, these life cycles parallel the cybersecurity life cycle. Cybersecurity for OT might be very recent, but safety life cycle, functional safety life cycle, process safety life cycle has been there for decades, or maybe more than that, 2 decades, 3 decades. So another reason is, uh, of course, we have different kind of attack vectors that is coming now. But if someone is very knowledgeable about the OT processes, they know the different parameters, how the OT operates, what are weakness in the design, what are the hazards inherent, right? A safety thing, or a hazard, or a or a simple mal-operation, right? Like, see, majority of the incidents that happen in OT industry are accidental. Somebody does something unknowingly, right? Accidents. but they have bigger implications in terms of when we talk about OT cybersecurity. And this is where threat agents might use that as an attack vector. For example, recently I had posted an article in my regarding ammonium nitrate explosions. I don't know how many saw that, I've heard that, right? And you should definitely read that. The reason why I'm saying is everybody must be aware about the Lebanon Beirut ammonium nitrate explosion, right? The impact radius, the number of people died, and the number of indirectly people were affected, and so on. That was due to incompetency of the port authorities, because everybody forget that was stored in the warehouse, and nobody even checked. There was no fire and gas monitors, no CCTV, nothing, no paper based trails, and nothing. But this is not new. Such incidents, if you read that article, has been these kind of accidents has happening multiple times across the world, and it's very deadly. The reason why we need ammonium nitrate is to make our fertilizer. It's an important ingredient for our fertilizer. And if you read regarding the explosions and why they happened, you will realize that those could have been easily prevented by certain basic policies and procedures. Unfortunately, we all act only when something happens, right? The reason why I'm talking about that is a purely a safety and procedural issue, but had a very deadly impact. Those things can also be uh, used as a vector to create an explosion using cybersecurity. It is possible. It is nothing is impossible, but it is much complicated. I don't think it is going to happen something immediately, but there's a possibility. We just need to be prepared. But ultimately, how OT cybersecurity works is whether the risks and its control measures or mitigations and countermeasures um, is lower than the cost of the event, right? If it is higher, it doesn't make sense. People normally observe that, okay, they'll um, take that risk and go. But at a basic level, you can do a lot of things to. You don't need sophisticated systems. So, like I was saying, this rapidly evolving field, as evidenced by various people requirement in different industries, a lot of researchers focusing on uh, control engineers and policymakers. What this says is OT cybersecurity is here to stay. The more complex systems become, the more OT cybersecurity need, and you need people at different level performing different things. And unlike the mature IT security field, OT cybersecurity roles and responsibilities are not still matured enough. Analyst role, one company might doing something else, and a different company might be doing something else. And there are many other things which we might discuss later as well, tomorrow or later during the Q&A if you have specific questions. Okay, so yeah, so when we speak about OT cybersecurity, the current situation is predominantly we are unaware about the risks and threat. So if you ask how secure is this organization, majority of the people may not have an answer, but they may not accept it, because then they have to face the wrath of the shareholders and investors and so on, right? This has become a board issue now. Do we have the right cybersecurity strategy for OT? God knows. Uh, Maybe we have a corporate ISMS in place, but do we have a OT CSMS, OT cybersecurity program or a management system? No idea. Can we accurately measure the breach risk? We don't have security policies, procedures in place, and how we can measure the risk or how resilient we can be. Similarly, how vulnerable we are in terms of vulnerabilities that we identify and so on, because that is important, right? Only when we do the risk assessment review, understand what assets we have, make an inventory, do a vulnerability assessment, manage the vulnerabilities, we won't know what is the potential possibilities. And this is where complaints, because of complaincy, people get broken into. It doesn't matter OT or IT. Ultimately, this is an attitude issue. How effective is our vulnerability management program? We might have good policies and procedures, but if it's not implemented well, uh, it's a failure. And ultimately, we have everything. We need to measure our benchmarks, right? We need to improve periodical audits. If we come across something, then we need to improve our management system. This can only be done when we have periodical audits, and when we have some findings. Having some findings is not a bad thing. It's not a negative thing. It's good. We can resolve that. If we don't resolve that, that could become $1 million issue or maybe more. So, what are the best way discuss about organizations security posture with the management? That's a very hard question, right? Management or the corporate people, they might want yes or no for an answer. It is not straightforward. It's complicated. Do we have trained resources? I don't think so. Majority don't. That's why we are here to share about all these issues. So, see, these industrial systems are typically there to monitor, report, and control the operation of the industrial process that we are discussing for so long. But what happens is these processes involves a combination of equipment and materials where the consequences that I was speaking earlier, right? It could, if it fails, it could range from a serious to severe catastrophe. As a result, a routine operation of these simple processes consists of managing risk. Simple as that. So we all know that risk is generally defined as the combination or product of threat and vulnerability and consequence, right? And threat and vulnerability is also um, responsible for the likelihood of that occurrence. So what happens is with the increased integration of these OT systems and enterprise systems, networks, the attack surface, and it has contributed to become more attractive target, right? It increases the threat aspect of it, and uh, organizations are increasingly sharing information between business and industrial systems. Well, the corporate networks are integrated to the OT systems, and yeah, I can go on and on actually. So see, another important aspect when we talk about OT, cybersecurity, or IT is this is still common. It's not only about the external threats. Sometimes people who are highly competent, who are at a level within the organization, they can maybe with a malicious intent or maybe even an accident, right? Like without knowing, they could do something and it could be a serious outcome there. We don't know. So that is the reason why we need people from outside doing the security testing, trying to find the number of the consequences and effects and so on. So all these factors, it's easy to see that there's a potential for someone gaining unauthorized access to an industrial process is rather become very straightforward. Majority of folks might know about Shodan, right? A shadow engine. It's like a Google search which index connected devices on the internet. If that information is available to you, the information is also available to the attacker, right? And right. So the vulnerability of industrial systems has changed as a result because of increased use of off-the-shelf systems and components and so on. But only when you fully understand the level of risk within your organization, it is possible considering the consequence element. So the consequence of failure or compromise of the industrial OT system has long well been understood by those who operate these processes. This is the reason why I'm stressing and sharing so much information with you guys. Because if you do not understand these processes, you may not be successfully defending or securing your organization. Hence, my emphasis on this. Threat reports as well. In 20, almost every other organization nowadays has a threat report. I wouldn't agree to all, but still, you should still read them, take it with a pinch of salt. But 2019, 2023, not much has changed. The challenges has only increased. So when we talk about the situation, the current situation, the trends with respect to OT cybersecurity, it continues to evolve. There are several trends that contribute to increased emphasis on OT cybersecurity systems. I'll just give you a few reasons and we can move on. Because critical infrastructure is the driving engines of the economy for a country. And nowadays, businesses have reported a lot of unauthorized attempts, right? Most of the cybersecurity vendors, they have this honeypot things to understand and find out how these attackers work and so on. So you go out there, search internet, you'll find out interesting reports and what people are doing. They are adapting. They have a lot of tools in their hands. So this is my next point as well. There are a lot of improved tools developed to automate attacks. We have generative AI. I had some screenshots, but I tried that with this recent chat GPT. It didn't work. But the previous chat GPT 3, version 3, you could enumerate a PLC, then you can ask it to develop an exploit using Metasploit. Now you can still enumerate the PLC, but you cannot develop the Metasploit. They have disabled that. So that is just one example. There are so many other tools available, right? And these are easily available. So the source of these threats from use of these tools is like they probably know more than how much you know about the industrial systems that you want to keep secure. So that is an important aspect. So we should never be complacent. Another thing is how business are working, right? So that is one thing. It's becoming more complex, and there's a lot of integration happening, digital transformation, cloud integration. Whatever you do, it must be taken into account when you're developing security for these kind of systems. Then another important aspect is insider attacks. That is something that still of lately frequently happening, right? Like basic policies purchases could have that's a low cost things that you need to do. Having expensive hardware and shiny solutions is not going to solve. So these and other trends have contributed to the increased level of risk. At the same time, OT security has been more significant and widely acknowledged. So this requires a more structured guidelines and procedures to define what is security is available to Intel system, and we need to act accordingly. And so it is a continuously evolving field. There's a lot of standards, good practices that is coming up. So when we talk about developing OT cybersecurity program, I don't want to go into more details because that might be too boring. But there was another image, something related to defense of depth. Maybe I'll share it tomorrow. But importantly, these are the three aspects: least privilege, defense in depth, threat risk assessment. These are what especially when you want to implement a cybersecurity program, you need to do. But there are other aspects as well. So what makes the ICS security different from normal security? So within ICS security, there is something called safety and security life cycle, reference model, system definition, system zones, security coordinates, foundational requirements, security level standards, regulations. So I'm not going to go into everything, just few of the categories. So there is a lot I can share here, but I think I'm already boring you guys. So the security lifecycle I was talking about, right? So IEC 62443 standard has a very good methodology to assess, develop, and implement and maintain OT cybersecurity. How you go about it? You start with high level. This is the assess phase. You have this high level cyber risk assessment. Then you identify all the assets. Once you identify all the assets, then you classify into different security zones and conduits. Then you do a detailed various countermeasures and mitigations, and yeah, this goes actually hand in hand, basically. Right, both are kind of similar actually, but talks about countermeasures, this talks about risk reduction. What do you do to reduce the risks? So you have different barriers in place. Maybe speaking about barriers, probably tomorrow I'll show you a slide that is something very interesting, might be of use to you. So once you do all this, then you procure the hardware, install it, test it, commission it, validate. Validation of cybersecurity is very important, and standard 2-4 speaks a bit about it. There are 13 practices that you need to do. So this is develop and implement phase. Then you have this maintain phase. This maintain phase talks about how you maintain, monitor, and do any changes. Management of change is very important, or change management, right? Very important. Then you need to be prepared for any situation. So what do you do when you have an crisis? How do you respond? How do you recover? What are the infrastructure resources you need? So this standard speaks about. So this is a maintain phase, and this is the policies and basically the periodic asset audits. Sorry, to touch when that talks about the audits that you need to do, and this talks about the various policies, procedures, and guidelines, or the technical recommendations that they talk about. 2-1. So this together helps you develop a cybersecurity management system. I guess that is more than enough for this slide. But I was talking about IEC 61511, right? Functional safety. Functional safety mimics almost the life cycle, almost the same. There they take cybersecurity as an input as well. So this is a reference model based on podium model. Podium model you guys might have already know. Level 0, level 1, level 2. So this is a very basic reference model. This is where your control systems lie. How you do. So understanding this, with an understanding of the importance of safety, security, the next step is to consider the nature of system to be secured. So in most cases, what we do is take a reference model that can be used to understand what is our system's functionality, and based on it, develop the necessary requirements and derive our own secured architecture, right? Which we'll see in the next slide. So the primary focus of industrial systems or the OT system security is on the lower 3 layers here. While the security here is usually addressed by the ISMS and so on. So yeah, so this is something that where you guys have to mainly concentrate. So when you develop a security program after the risk assessment, something that you high level risk assessment, something that you do is you do the network segregation. So here we have high level process industry. This is a process industry where we have different zones and conduits. So normally conduits could be a switch, could be a physical cable, fiber optic cable, a router, a switch, and so on. Zones are particular areas, right, within a network. So this is one zone, this is one zone. This is a simplistic model. This is one zone, and you have a conduit here, you have a conduit here. So earlier, sometime back, I was talking about safety system, which is kind of air gap, right? This is a safety system that I was talking about. It's called safety instrumented system, right? This is safety PLC. The safety PLC takes some critical decisions, and if you see, it is not connected via Ethernet, or it is not in the same network. It is RS485 Modbus serial communication. So this is a non-routable protocol, so you not have to worry about the security aspects that go in with the Ethernet IP, TCP connections, right? So, and another thing when you develop this is the data flow. How does the data flow? So that is something that you need to know, right? So yeah. Right. So I guess okay. Okay. So this is one of the very important aspects, especially when you um, do the network segmentation, identify different zones and conduits. Then you have micro segmentations. Then you have virtual LANs and so on. Right. Um, this is a simple model for a process industry. Process industry and manufacturing industry have little bit differences. So this is for a manufacturing industry, um, where they have different networks within the plant, and that is what you have: network 1, network 2. You might have multiple networks. Then within the DMZ you have different applications, workstations, MES, inventory management, right? The manufacturing is different from process. So here you have inventory and MES, which have different layers. The SCADA, you might have seen that SCADA 112, ISA 112 architecture. But yes, that is a bit different. But yeah, manufacturing has its own set of requirements that you need to be aware of. So again, the reasons why I'm just limiting to the reference model, and these are the most important aspects. But again, this is just a start. Uh, then you have this foundational requirements. Okay, are not listed here. There are 7 foundational requirements, and each foundational requirements has its own additional requirements enhancements. So when we talk about foundational requirements, it's identity and access management. It is data integrity. Then you have data confidentiality, timely response to events. Then resource availability and so on. So those foundational requirements are the cornerstone of a cybersecurity program as well. And that the product security has something similar to that, but it is built upon the foundational requirements as well. So that is something very important for you to know. So this network diagram that you see is a simple example depicting different zones and conduits for the processes and manufacturing respectively. So with this, we bring this session to an end.